All right, so let's go ahead and begin today. So today we're going to talk about what a shift register is, and then sequence detection. So first, the shift register is actually part of the final project individual. Like I mentioned at the beginning of the quarter, and it's on Canvas in the syllabus, the final project actually has two parts to it. There's an individual part and a team part. And Tuesday of next week, I'll talk more about the final project. I mean, most of the information is already up on Canvas, but I'll talk about it and point out, some particularly important things about the final project. But the shift register is part of the final project's individual. And then sequence detection, that's what you need to do for lab 6. Okay, lab 6 will be due Friday of next week. As hopefully you're aware, lab 5 is due tomorrow. So hopefully people are working on that or close to finish or finishing it. Okay, you'll have time after the activity today to work on your labs. So the first thing about shift registers is that there's two types. Okay, these are acronyms. SRR stands for shift right register, and SLR, you may guess, is shift left. And what we mean by shift right here is that the data goes from most significant bit the least significant. Okay, if you think about it, usually when we, using least significant bit, most significant bit, least significant bits on the right, most significant bits on the left. So the data is moving most significant to least significant, right? Going to the right. Okay, so that's where the name right comes from. So you can probably guess how the data is going for shift left. What do you think? Yeah, just the opposite, right? The data for shift left goes from least significant to most significant. Okay. All right. So I think the best way to learn how a shift register operates is just by going through an example. So I've got a couple of examples up here. One of a shift right and the other a shift left. Now, shift registers, just like registers, just like FSMs, just like any sequential type of device or circuit, it's either rising edge trigger or falling edge trigger, like we talked about before. Okay, so I made the shift right register here rising edge, and I made the shift left register falling edge, but you could have the reverse. I just picked one type and the other type just for sake of example. Okay, but let's say, the other thing I should point out, because you haven't seen this notation before, I don't think. This notation of a rectangle with these squares within the rectangle, that's notation for a register, right? So the rectangle represents the register, and then each square represents an output of a flip-flop that's contained within that register, right? We talked about how registers are just multiple flip-flops. So you can see here that there's 8 squares, so there's 8 flip-flops. Okay? So this is an 8-bit register. It can store 8 bits. Okay. So let's say that this is our initial data in our shift register. All right, most significant bit is 1, 1, 0, 0, 0, 1, 1, 0. With the 0 here being the least significant bit. And then this here, this is an input to the shift register, and DR stands for data right. So when we're shifting right, this is the data that's going to come into the shift register. Okay, and I made it a 0, but I could have easily made it a 1. You can make this into either a 0 or a 1. Okay, so what's going to happen is on the 0 to 1 transition of the clock. So this is the clock here. So at the time of the 0 to 1 transition of the clock, that's when the shift right is going to happen. And when that shift right happens, the data on this DRN, that data is going to go into the most significant bit of the shift register. And then all the other bits are going to shift over one place. So you see this one would come over here. This one would come over here. This 0 would come over here. This 0 would come over here. This 0 would come over here. This one would come over. This one would come over. And then this last 0 here would fall off the face of the disk. Okay, there's nowhere for it to go. So it's essentially not be there any longer. Okay, so if we start off with this data and we do a shift right with this bit coming in, this is what we would end up with after this 0 to 1 transition of the clock. Okay, because shift registers are synchronous devices. Okay, they depend on the edge of the clock.
What is the
DRN is just an input to the shift register, and DR just stands for data write. So when you're shifting right, the data on this input that would come into the most significant bit. You're going to see in the next example, there's a DLN, that stands for data left. So that's an input for when you're shifting left. Okay. And as we're going to get to in a little bit, typically you'll have what's called a universal shift register that can either do a shift left or shift right, depending on what some select bits are equal to. And we'll get to that. Okay. Okay, so any questions about this example? Because if this makes sense, the shift left is just the same thing, it's just that you're going the other direction. Okay, because if you look at this next example here, okay, this is our initial data. We're shifting left, it's a falling edge trigger. Here's the input on the data left in. Okay, so that's the data that's going to come into the register. So since this is a falling edge, the shift is going to happen on a 1 to 0 transition of the trigger. Okay, so at this time, the data on this DLN is going to go into the least significant bit of the shift register, and then all the other bits are going to shift over one. So this one comes over here, this 0 comes over here, this one comes over here, this one comes over here, this 0 comes over, this 0 comes over, this 0 comes over, this one comes over, and then this 0 again would fall off the face of the earth. No place for it to go. Okay. So any questions?
So the DR of the DLA, is that telling it to shift left or shift right, or we're saying that's what it's called is like,
Yeah, I know what you're asking. The quick answer is no, these are not determining which direction you're shifting. There's actually another input that decides that, and it's actually called a select input that we're going to get to. All these inputs just have the data that's going to go into the register.
Okay.
Yeah, but yeah, whether it's shifting left or shifting right is determined by a different that I'm not showing here. Okay. Yeah, that's a good question. Okay, so this is just basically how a shift register works. Okay. Now, one thing that you can use a shift register for, and there's many other uses besides this, but this is a common use, in that you can use a shift register to do multiplication by a whole number power of 2 or division by a whole number power of 2. Okay, and an example of this is, let's say we start off with this binary here. Let's say these 1s and 0s are representing a number. Okay, that this is a binary number. So what would this be in base 10? 1100 binary is what in base 10? What is it? 12, right? Because we don't have a 1, we don't have a 2, we got a 4 in it, right? So this would be 12. So let's say we take this binary 12 and we shift it one place to the left and bring in a 0. Right? So if I shift over one place to the left, and then I bring in a 0, now what does that binary number become? 24. 24, right? Because I don't have a 1, don't have a 2, don't have a 4, I have an 8 and a 16. So by just shifting one place to the left and bringing in a 0, we're doing it times 2. I'll get to your questions in a second. If we did another shift, right? If we did another shift left, bringing in a 0, what number is that? What is it? 48. Right? Because no 1, no 2, no 4, no 8, 16, 32, 48. So to multiply by whatever power of 2 you want, you just got to shift to the left the appropriate number of bits, right? You shift left 1 times 2, twice times 4, 3 times 8, and so on. What's the question?
This example, I can make like the initial value like 4 bits, like with 0 standard, because it's right and not wrong.
Well, you're right that you've got to be concerned with running out of bits depending on like what your range is. So yeah, if you let's see, if you only had 4 bits, you could only let's see, let's say you had 8 bits. Like if we started with this and there was, the assumption here that, if this was 8 bits, like you said, this would have to be 0, so the value doesn't change. Well, if I only have 8 bits and I'm starting with this number, I can only shift 4 places before I would run into a problem, right? But if that was a problem, I could just get a bigger register. I can get a register of however many bits I want. I mean, it's just adding more flip-flops, so it's not really a limitation. But it is something you got to think about, because whatever you have, that is setting a limit. Okay, does that answer your question? Yeah. Okay, well, if this makes sense, right? Shifting left gives you a times by a whole number power of 2. What do you think we do to get a divide by a whole number power of 2? Yeah, you just shift the other direction. You just shift right. So, if you started out with a binary 12 and you shifted one place, bringing in a 0. Oops. Right, we would go from 12 to 6. Right, we did another place. Go to 3. And you see, this is the problem we would run into that William is mentioning, because if we wanted to do another, divide by, let's see, we did divide by 2, divide by 4, divide by 16, we ran out of bits here, so we would need more bits to do that. Okay, so yeah, you are limited by the number of bits you have as far as how much you can multiply or divide by. Now, when you take CPE133, you'll see in that class that there are instructions to your microprocessor that are shift left or shift right instructions. And you'll learn a different type of coding in that class than what you're used to, what you've done previously anyway in your curriculum. And that's what's called assembly language. And assembly language are instructions that are close to the hardware. Okay, and what I mean by that is when you look at an assembly instruction, it will have something like, move this data to this register. Take the data in this register and invert it. Add 1. Right? Keep coming. Or it would have like, shift right this many bits, bringing in a 0. Okay, so you'll see when you take CPE133, you'll see that you'll actually do some programming where knowing this is helpful. Okay, because you might want to divide something by 4, and the easiest way to do it is, well, shift to the right 2 places. Okay, so any questions up to this point? All right, well, the next thing is this universal shift register. And what's meant by a universal shift register is that it can do shifting either direction, and also it can act like a memory register. Okay, so a shift register, it can shift, or a universal shift register, it can shift left, it can shift right, it can hold data, right? It can store data. And you can load it. Load data. When I say load data, that's the same as when we were talking about a memory register and when Q equals D, right? When the Q outputs equals whatever is on the D input. That's what we mean by loading a register. And you see this universal shift register, it has a Q output just like a memory register does. It has a D input, okay, just like memory does. It can have, definitely have a clock because any sequential circuit has a clock. Typically they have a clear, but you see what a universal shift register has additionally is this input here. That's a select input. And for this universal shift register that I'm showing, that select input is 2 bits. So if I have 2 bits, how many values can I represent with 2 bits? 4. Okay. And it's not by coincidence that it can do 4 different things. Okay. That's why we need 2 bits. So now if you look on the table, there's a handout that has system Verilog code for a shift register. Okay, universal shift register. And the top part of that code is stuff you've seen before, so that's why I can write it down here. But what I wanted to focus on, to talk about, is the code that goes with the else of the if statement. Okay, so if you look at the handout and you look at where the else is, you'll see that there's a case statement. And that case statement is sensitive to the select input, right? So whenever that select input changes value, that's when this case is going to be evaluated. Well, first, look at case 1, right? If we choose with the select 1, right, 0, 1, Q is going to be assigned to whatever's on the D input. So you see, this is when we would be loading the shift register. Right, that's just like when you enter data into a memory register, like we were talking about. Load, enter, enable, all the same thing. Okay. All right, let's look at this case 2, right? So this is when we make select, binary 1, 0, right? A binary 2. Well, let's look at this system Verilog code here. Here, the Q output of the shift register is being assigned inside braces these 7 bits along with this single bit that's a 0. Okay, first of all, who can tell me what braces mean in system Verilog? Yeah, concatenation, right? And then what does concatenation mean? Like when we concatenate, what are we doing? Yeah, you're just joining things together, right? So you see what happens here is that these 7 bits, okay, and remember, we number the least significant bit 0, and the most significant bit is the highest number, right? And since this is 8 bits, right, the most significant bit will be number 7. So you see what this code is doing is it's taking these 7 bits, right? It's taking bit 6 through bit 0, and it's attaching a 0 to the right of it. So essentially what happens, you're taking these bits and you add a 0 here. Okay, which is what type of shift? You're shifting left. Okay. See, this would be a shift left. See, that's the Verilog code to do a shift left, 1 place, bringing in a 0, which would be a multiply by 2.
So when you do this isn't having a data right and or data left. Right? This is just zeros only.
Right. Yeah, this would be like, let's see, we're doing a shift left here. So that would be like DL underscore ND, fixed 0.
Yeah.
Like we would connect it to 0.
All right.
Yeah. All right. Well, if that made sense, what do you think option 3 is doing? This is shift left. What do you think this is doing? Yeah, see, shift right, because this is taking bits 7 through 1, right? So it's taking these 7 bits and it's joining a 0 on this side, right? So it effectively shifts it right. So this is a shift right. Okay. Notice option 0 is missing. Why is option 0 missing? Can you guess why? You look like you want to say something.
It's kind of like when you're dividing, because if you kept it a 0, then it would keep it the same value.
Well,
Right.
this 0 here in this option, that's just determined by what we have on the select. Like the 0 that's coming in or out of these registers, it's not shown on this because it's essentially just fixed to 0. Like this universal ship register doesn't have like a DRN or DLN because it's just sort of being fixed to 0.
Okay.
But if we leave something out of a case statement, or if we leave something out of an if statement, what does Verilog do? Yeah, that's how we're creating the latch. That's how we're creating the memory. That's how we're getting the hold state. Okay, so you see, option 0 is your hold or your storage. Also, what else is missing from this case statement? Yeah, there's no default. Is there a reason why you wouldn't want the default? Because in a case like this, we want the default not to be there. It's probably one of the rare circumstances that you don't want to have a default. And can you guess why?
You don't want anything to happen.
Yeah, see here, we want the default to just store data. We see if we put a default where we're assigning Q to something, we don't know, if we assign it to some data, we don't know if that's going to have some adverse effect on, whatever this ship register is connected to. It's better in this case that if you have some sort of case that's not accounted for, that you just keep what you have. Because if you change it, you could make things worse. Okay. So yeah, here's a case where you wouldn't want a default. It's a rare one, but there's some cases where you don't want it, when you just want to keep whatever was there. Okay. All righty. So any question now? There's going to be an activity today, and the activity is you're given a universal ship register just like this. Now, I think the one in the activity does have a DLN and a DRN, so it's just that they're not fixed to 0 like this is. But you're asked to do a timing diagram, and in that timing diagram, sometimes the universal ship register is shifting left, sometimes it's storing, sometimes you're loading it, sometimes you're shifting right. Okay. Once we're done with the rest of the lecture up here, I'll on the screen, I'll show you the activity and point out a few things in that activity. But if you understood this, I think the activity shouldn't be too difficult. Okay. So, but before we go on to something totally different, because sequence detection is a totally different topic than ship registers. Is everybody okay with ship registers up to this point? You'll get some more practice with it.
With the DRA or DRA and DLN, you make like 2 separate inputs for them.
Yeah.
Like another spot.
No, it'd just be 2 separate. Yeah, exactly. Yep. Okay, any other questions? All right, so let's talk about sequence detection. And this you need to know for lab 6. Let me turn the camera. I have to turn it that much today. That much. There we go. All right. Okay, so sequence detection. This is important for lab 6, which again isn't due until a week from tomorrow. And the first thing to know about sequence detectors that do sequence detection is that there's 2 types. Okay, there's resetting sequence detectors and there's non-resetting sequence detectors. And here's the difference between the 2. And in both of these definitions, the first 3 words are very important. See, a resetting sequence detector after we have a detection. Okay, this is very key. After we have a detection, no prior bits can be part of a subsequent detection. Okay, so, we get a detection, and then for any detection after that, you can't use any bits that was part of that first detection that you have. Okay? A non-resetting, it's still after a detection. Now, everybody, you all know what the double dashes mean. I'm just repeating, right? I just didn't want to write the same thing over again. So after a detection, just like up there, when it's non-resetting, prior bits can be used for a subsequent detection. Okay? So that's what the difference between the two is. In one case, after a detection, you can't use previous bits, right? In the other case, after a detection, you can use previous bits. Okay? And again, the key word here, keywords, is after a detection. Okay? When we start looking at a state diagram for a sequence detector, I'll come back and emphasize this again, because if you miss these three words, it can cause confusion, or cause more confusion, I guess. Okay. All right. So the next thing is, and hopefully this will illustrate the difference between the two. These are the definitions. Now I want to give an example that hopefully illustrates the difference between the two. So let's say that this is the sequence we want to detect. For whatever reason, we want to detect 1, 0, 1, 1. And then let's say we just have this long string of bits. This is like T for the 0, and as time progresses, these bits on some wire or some output are just changing as you see here. Okay. All right. Well, if you have resetting, your first detection. Let me get my different color marker here. Okay, so if we have resetting, we're looking for 1, 0, 1, 1, 1. We're going to have a detection here, right? 1, 0, 1, 1. We're going to have another detection here. Okay, we're going to have another detection here, right? This 1, 0, 1, 1. Well, now if you look, we have another 1, 0, 1, 1 here, but because this is resetting, I cannot use a previous bit in a subsequent detection after I've had a detection, right? See, I have a detection here. So now I can't use any of these bits in a subsequent detection. So this 1, 0, 1, 1, if it's resetting, that is not a detection. Okay? Okay, now if it's non-resetting, if it's non-resetting, I still get a detection here. Just like in the resetting case, I still get a detection here. I still get a detection here. But now if it's non-resetting, because I can use previous bits after a detection, I have another detection if it's non-resetting, because this 1, 0, 1, 1 would be a detection now for non-resetting, where it wasn't for resetting. Okay, so does that make sense? Based on what we were talking about, do you see the difference between the two? Okay. I realize when you're talking about like a flip-flop or a register, resetting means outputs go to 0, but resetting doesn't mean that in this case. Resetting means exactly what we have written here, what we're showing here. It's one of those, happens all the time, and especially engineering, right? You have a word that means different things in different contexts. Okay. All right, so the next thing we're going to do, getting all my colors, lots of different colors today. Okay, the next thing we're going to do is we're going to come up with a state diagram for a sequence detector to detect this 1, 0, 1, 1. Okay, and this is something, in fact, this is the first thing you'll need to do for lab 6. Okay, the first thing for lab 6 is coming up with a state diagram or diagrams for the sequence that we want to detect. And then once you have that state diagram, like we talked about last class, you can put it into the code format I gave you to design an FSM. Okay, because lab 6, you're designing an FSM that does this sequence detection. Okay, not this example we're doing here. It's a different sequence, but again, you get the idea with this one. It should help a lot with one you have to do for Lab 6. Okay, now, like I said last time, all state diagrams, you need a legend. Okay, I think there was a few groups that in the activity last time, they did the diagram correctly, but they didn't include a legend. I think I took off 1 point, but it's important to always include a legend with whatever state diagram you have. Okay, so remember, in our state diagram, the circle represents the states. Okay, and we just have our name, and you can see I named these letters A, B, C, D, E. Okay, what goes here? Like Z, what is Z? Because what always goes inside the circle in this place? Right. Z is a more output, exactly. Okay, so Z, more output. Okay, it only depends on the state. And what Z represents here is Z is the output to your FSM. And when Z equals 1, sequence has been detected. So sequence detected. All right, so Z is 0, it means we haven't detected the sequence yet. Z equals 1, the sequence has been detected. Okay? Okay, then we have this X by the arrow. Remember, the arrow represents the clock transition. X is an external input. And here, X is the sequence, or X is the series of bits. Like in this example here, this was X. Right? So X is just a series of bits. It's a series of bits that we're looking at to see if we have this sequence. Okay? All right, so let's start with our state diagram. So you can see here I have 5 different states, and again, I just lettered them. A is where we're going to start. Okay, so since we're starting here, we don't have a sequence detection, right? So Z is going to be 0. And if we're in this state, right, A, our starting state, and we get a 1, right, which is the first bit in the sequence we're looking for, well, then we're going to progress to state B. Okay. And then when we're in state B, we've only detected this first bit of our sequence that we're looking for, so we haven't detected the whole sequence yet. So Z is still 0. Z only becomes a 1 once we've made the detection of the sequence we're looking for. Okay, now if we're in state B and we get a 0, which is the next bit in the sequence we're looking for, we're going to progress to state C. Okay, so we're going to go to C if we get a 0, and we haven't detected the sequence yet, so Z is going to be 0. Then if we get a 1, we'll go to the next state, because that's the next bit in the sequence we're looking for. But we still haven't detected 1, 0, 1, 1 yet, so Z is still going to be 0. And then in state D, if we get another 1, well, now we detected the sequence, right? Because we got 1, 0, 1, 1. So in state E, that's when the Z output would change to a 1, because we've detected what we were looking for. Okay? Now, this is the easy part. The tricky part of doing state diagrams for a sequence detector is where you go when you don't get the bit that's next in your sequence. Okay, and that's what we're going to do next. Now, before we do that, what I like to do, and this isn't something like required, like a lot of people don't have to do this, but what I like to do, because it helps me figure out like what state I need to go to if I don't get the next bit in the sequence I'm looking for, is by each of the states, I write what it took to get. Okay, now A is where we started, so it doesn't take anything to get there because that's where we started. But to get the state B, we needed a 1. So I'm just going to put a 1 there. Okay. To get the state C, we needed a 1, 0. To get the state D, we needed a 1, 0, 1. And to get the sequence, well, it's the 1, 0, 1, right? In state E, we needed the 1, 0, 1, 1 that we're looking for, right? Because once we're in state E, we detected our sequence. Okay? All right, so now let's think about what this is going to look like, what our state diagram is going to look like when we don't get the next bit in the sequence. So let's say that the first bit we get, instead of getting a 1, which is the one we're looking for in our sequence, let's say the first bit we get is a 0. So we're in state A, and instead of getting a 1, we get a 0. What do you think we're going to do? Just stay in state A, right? Because if my first bit is a 0, I can just wait there until I get a 1. Right? So you see, I would just stay in state A if we get a 0. Okay, so now we're in state B. Let's say we get a 1, and now we're in state B. But here in state B, instead of getting a 0, let's say we're in state B and we get a 1. What do you think we want to do in that case? So you know, we've gotten a 1, right? But now we get another 1. Just stay in B, right? I can just stay in B until that 0 comes along, that first 0. Right? So you see, we would just stay in 1. Okay, everybody making sense so far? All right, so now we get to state C, right? It took a 1, 0 to get here. And to progress on in our sequence detection, we need a 1. But let's say we're in state C and we get a 0. So it took a 1, 0 to get here, but now we get a 0. And we're looking for this. What do you think we do in that case? Yeah, why would we go back to A? That's correct, but why? Yeah, once you get 2 zeros in a row, you're not going to get this sequence, right? You got to start over again. Right? So yeah, if we're in state C and we get a 0, we want to go back to state A. Because we just want to start over again in that case, right? Because we don't have 2 zeros in a row in the sequence that we're looking for. Right? Okay. So now we go to state D, right? And to get to state D, we needed a 1, 0, 1. And if we get a 1, well, that's what we're looking for, right? That's why we go to E and Z turns to 1. But what if we're in state D and we get a 0? Ah, very good. Why is it C?
Because now we have 1, 0. and
Yeah.
it's already-
That's what it takes to get to C. So you see, if we're in D and we get a 0, we want to go back to C. Okay. See, it can be tricky. It can be tricky, right? But you just got to kind of figure it out. You know, that's why I think writing down what it takes to get each of the states helps out. It helps out when you got to think about, well, where do you go when you don't get the bit that's next in the sequence? Okay. Now, here's a really important question I'm going to ask you, okay? Because this is where people can get messed up, all right? And that's what we just did right now. Like, we haven't finished this yet. We're going to finish it. But for what we have right now, is this for a resetting or non-resetting? How many people say it's resetting? How many people say it's non-resetting? How many people don't know? How many people think this is a trick question? Why is it a trick question? It's both. It's both, because these don't differ until after a detection. See, before a detection, it's all the same. These only differ after you have a detection. See, what you're going to see is this state diagram is different once we've gotten to state E, because state E, we have a detection. Okay? See, that's one of the most common errors when people do this, is they think there's some difference between these two before a detection, but no, it's only after a detection that these differ. Okay? That's a really key point. All right, so let's see, and let's finish this. And let's see, I need my other colors here. Let's see, we'll do red. Okay, we'll do red for reset. Okay, so we're doing resetting. So remember, resetting after a detection, no prior bits can be part of a subsequent detection. So we get the state E where we've had a detection. And now let's say we're in state E and let's say we get a 0. Right, so we've had our detection and we get a 0. Where do we go? Where would we go? It takes a 101 to get to B. Yeah, just be back to A, right? Because remember, the first thing we're looking for in our sequence is a 1. So if we get a 0, we're still looking for a 1, right? Because a 1 takes us to B. So yeah, we would just go back to A. Okay, so we're still resetting. And now after a detection, we get a 1. It would be B, right? Because it takes a 1 to get to B. So you see, this would be a 1. So what's in black and what's in red? That would be the state diagram for this sequence for a resetting. Okay, so any questions on what we did here? Everybody see why this goes back to A, this goes to B? Okay, now let's do orange for non-reset. But remember, non-resetting, I can use prior bits for a subsequent, after a detection, I can use prior bits for a subsequent detection. So let's say, we have our detection, right? And now let's say this is a 1. We get a 1 after our detection. Where would we go? To B. To B again, because it takes a 1 to get to B. So you see, this would also go to B. Okay, all right, now, again, it's non-resetting, so I can use prior bits, right? After a detection. Well, now what if we get a 0? Very good, C, right? Because since it's non-resetting, I can use this 1 of the previous detection for my next one. So now I can use the 1, 0, and it takes a 1, 0 to get the C. So that's where I would go. For me, if it's non-resetting and I get a 0. Okay. So if you understood what we just did here, then what you have to do for lab 6, it's a little bit more involved, but it's the same thought process. It's the same approach. Okay. So any questions?
You explain to me why we went from D back to C.
Oh, D to C?
Yeah.
Okay. All right. So to get to D, well, first thing, does it make sense to you to get to D, we needed 1, 0?
Yeah.
And it makes sense to you that to get to C? Okay. So here we are at D. Now, if I get, let me go back to black. 1 we progress on because, it's part of the sequence. But if I get a 0, well, look, 1, 0, 1, 0, 1, 0, that's the first 2 bits and what I'm looking for.
Oh, so we have like a beginning again.
Right.
Okay.
See, again, that's why writing down what it takes to get to a certain state, I think helps, right? Because I can go, oh, 1, 0, 1, 0, this is where I need to go.
Gotcha. Okay.
Yeah, to tell you the truth, when I do these state diagrams, if I don't write down what it takes to get to a particular state, I drive myself crazy. Because if I don't write it down, I'm looking, and sometimes it seems like, oh, if it's not this bit, I should go to this state. To me, when I write these down, it becomes crystal clear. Yeah, with some practice. I practice it, so it'll take some time. But. All right, so that's what sequence detection is. Now, what I have left to show you, there's a couple of things on Canvas that I need to pull the screen down for and turn the projector on to show you. Then I just want to talk about a little recap of what's in the syllabus about what's left the next 3 weeks. But everybody fine for me to pull this down, put the projector on. Great. All right, so first is the activities, which again involves a universal ship register. So you have this universal ship register, you know, it's a Q output, D load, that's the D input. Yeah, and this has a DR in and a DL in clock, and then it has a select line, which again is 2 bits. And just like in the example we went over that you have the code for, when the select is 0, it's hold or storage. 0, 1, parallel load means the same thing as load. That's when Q is going to equal the data that's on the D input. When the select is a 2, it's going to do a right shift. When it's a 3, it's going to do a left shift. This is rising edge, propagation delays. We don't talk about, so you don't have to worry about them. And it says don't worry about them anyway. And then also note that it tells you that the initial D out is 45 hex. Okay, so that's what it starts with, 45 hex. But like any timing diagram, you want to progress from the left to the right. And since it's rising edge, you're going to look at what's occurring at all these 0 to 1 clock transitions. So, you know, you look at what the select is, and that's going to tell you what the universal shift register is doing. Maybe it starts off with a load, then it does like a shift right, you know, and you just progress through. Okay, and there's 2 examples. Okay. So I think it's fairly straightforward if you understood what we did earlier, but of course, like always, if you have questions when you go through it, please ask. You know, you will have to convert from hex to binary and back from binary to hex, right? Because we give you the values in hex. So when you do either a shift left or shift right, you know, take the hex, convert to binary, do the shift, and then just convert back. Okay. Also, I wanted to show you that. Okay, so you can see here there's 4 modules, but you only create 1. Okay, 3 of these modules are given to you. The only one that you create is the FSM. So this is the FSM that's going to do the sequence detection. Clock divide, sequence driver, and this BC deck. Dr. Mealy designed those modules, and the files, the actual files, not the text, the actual files that you need are on campus. In fact, let me show you. If you go on Canvas, right here where it says lab resources, in fact, it's right where the universal seg text is. Here's the sequence driver, the clock divider, BC deck. Now, when you look on Canvas and you have a better view of this, you're going to see that the suffix of these files is BHD. That's because these files were written in BHDL, okay, which is a different language than Verilog or System Verilog. It's totally different. But in Vivado, you can run files of different languages. Like you can run System Verilog with Verilog, you can run System Verilog with VHDL, you know, you can mix them up. So all you need to do is download these and, you know, have them as part of your project for Lab 6. Now, there is one modification that you'll have to do to the clock divider that I'll show you when I show you a video coming up. Okay, but these are where the files are at. Okay. So if we go back to the diagram, okay, what these modules that Dr. Mealy designed are doing, Well, first of all, the clock divider, we went over a clock divider last class. What does a clock divider do? Yeah, it just slows down the clock. So, here's your 100 megahertz coming in. Now, this BC deck module, Dr. Millie's, does operate on the fast clock. See, it goes directly there. But to your sequence driver and also your FSM, that's going to be operating at the slower clock. Okay. Now, what this sequence driver does, and if you take a look at it, on the input side, we have 8 switches, okay, representing 8 switches on your basis board. On the output side, you have an output going to 8 LEDs, and then you have another output, a single bit output that's going to the FSM X input. Well, what this sequence driver is doing, it's taking the bits that you determine by the switch positions, and it puts that into a data stream just like this. Like it takes those, 8 bits that are on the switches, and it puts it on one output in a serial fashion. Okay, so coming out of this sequence driver is something just like this, just a string of zeros and ones. And that's what's going into your FSM. So it's that stream of bits where you're looking for a sequence. Okay, you're designing the FSM, to look for a particular sequence. In fact, you're designing it to look for 2 sequences. Okay, that I'll explain more coming up. Now, the output of your FSM, and again, this is just a single bit output because this is Z, right? Z, just like in our example, is just a single bit. When it's 0, it means we haven't had a detection yet. When it's 1, it means we have a detection. And that single bit FSM output goes to this BCD deck. BCD deck is a module that drives the displays in a fashion that Dr. Mealy came up with. And, students that have taken this class in the past, they call this the cool crap module. And that's because the way Dr. Mealy designed this is when you have a detection, it will display cool. Okay, so when this is a 1, it displays cool. When you don't have a detection and this is 0, it displays crap. Okay, now why I chose those words, I don't know, but it's Dr. Mealy. Okay, but that's all this module is doing. It's just showing 2 messages based on what this input is, whether it's a 0 or 1. Okay. Okay, let me show you. This is one. Okay, so this is what you'll be designing. Okay, the FSM, we want you to design a resetting more type FSM. And we want you to look for 2 different sequences based on whether a button is pushed or not. So when a button is pressed, we want you to look for this sequence, 0, 1, 1, 1, 1, well, 0, 1, 1, 1, 0, 1. And when the button's not pressed, the sequence to look for is 0, 1, 1, 0, 0, 1. Okay. Now, when you take a close look at this, you'll see that these 2 sequences only differ by 1 bit. Okay, the only bit that's different is the 4th bit. Okay, but still, you're looking for one of the sequences when the button's pressed. You're looking for the other sequence when the button's not pressed. So there's 2 approaches to this, and I've seen both of them work. One approach is just to do one state diagram. Okay, so in one state diagram, you're showing both sequence detections, the paths. The other way to do it is to do 2 separate state diagrams, one for this sequence, one for the other sequence. Okay, so however you want to do it, it's up to you. I've seen both of them work. Personally, I just did a single state diagram because these only differ by 1 bit. So the state diagram is essentially going to be the same for both sequences, except there's going to be a little part of it that's different since that 1 bit is different. Okay. But anyway, like I said, you can either do 1 state diagram or 2 state diagrams, but that's where you start. You don't even think about writing any Verilog for your FSM until you have your state diagrams. Or diagram, depending on whether you need 1 or 2, okay? Let's see, was there anything else I wanted to mention about this? Oh, I want to show you the video that shows it.
So you're detecting a 6-bit sequence. How long, like how many switches are we looking to?
Well, there's 8 switches, but you'll see in the video coming up that, you know, I can set my 8 switches and maybe the sequence I'm looking for is the middle 6.
Yeah, I was just wondering
Yeah.
if we're like bigger.
Or it should even work when they, like when they're discontinuous, like, you know, you got your 8 switches, but maybe these 3 are part of the sequence and maybe these 3 over here. Like it should be able to pick it up wherever within those 8 switches the sequence is, it should be able to detect it.
Does the sequence divider send it like over and over? That's why.
Yeah.
Okay.
Yeah, exactly. Yeah, this is just gonna keep cycling. And the LEDs, as you'll see in the video, the LED like tells you like where in the, you know, like what switch is being looked at. Yeah, let me show you the video and maybe it'll become clearer. But yeah, I made a video of a working sequence detector. So I think this is when there is, yeah, see, is a sequence. So after it goes through the switches and it finds the sequence, you see that the message changes. And notice the rate of the LED. I'm going to comment some more on that in just a minute. Now, this video does not show all the test cases. Okay, I only show 3 of 4 test cases. So now I made it so it's not detecting the sequence with the button not pressed. So you see it doesn't go to cool. And it is the sequence for the button when it is pressed. So you'll see once it goes through, it'll change. But like I said, I only do 3 of the 4 test cases because I don't show the case where when the button's pressed, it doesn't detect. Okay. Now, the reason why I wanted you to see the rate of the LEDs is because the clock divide that Dr. Milley has, now it's written in VHDL, which again is a different language than, you know, what you've used. But that module, just like the example I gave you, the rate at which the LED is going to flash, you know, based on the frequency that comes out of that clock divide, is determined by an integer that's in that VHDL file, that clock divide VHDL file. So you're going to have to modify that number because if you don't modify the number, this LED and the display changes too quickly. Okay, if you don't change the number, when you get a detection, it just like flashes. You can't even make out that it said cool. Okay, it's so fast. And also the LED is just going, you know, it's racing. Okay, so I'm not going to tell you what to change that integer to. You're going to have to figure it out. Now, there's no one answer. You know, we're not saying, you know, make it a certain frequency. We're just saying use an integer and get a rate that's somewhat like this, you know, around this, you know, speed. If it's a little faster, it's okay. If it's a little slower, but if it's really fast or really slow, you know, you got to kind of use your judgment. Okay, but I wanted to give you an example of what to look for. Okay. Let's see. Was that all that I wanted to talk about? Oh, I want to talk about the next 3 weeks here because we're getting down to the end of the quarter. So I just wanted to make sure everybody knows, you know, what's coming up the next few weeks. So is everybody okay? Can I turn this off and put the projector or the screen up? Okay. Okay, so most of what I say here is already in the syllabus, and I talked somewhat way back at the beginning of the quarter, but I realized, you know, it's been some time, and we got other classes and stuff, so I just wanted to point out, you know, some of the main things left. You know, first of all, next week, Tuesday, that's the last lecture. Okay, that's the last in-person meeting. Remember I said at the beginning of the quarter, this is a blended class, so like the first 15 meetings are in person, then the last 5 are not in person. I say they're online only because most of the time I'm available on Zoom, but we're not having any online classes or online lectures or, assignments or quizzes or anything like that. So on Tuesday, the last lecture we have, I'm gonna talk about binary multiplication. We talked about how to multiply by a whole number of power 2, but we're gonna talk about, well, what if you want to multiply by 3 or 7, or, something other than a whole number of power 2. And that's gonna bring up something called an accumulator, okay, that we'll go over. We got the code for that, so we'll kind of look at the code and talk about in general what an accumulator is. And then I'm gonna talk about the final project. And as I've mentioned a few times, the final project has 2 parts to it. There's an individual part and there's a team part. The individual part is the 4-bit binary multiplier. Like everybody does that individually and turns in their own work. Then the project, 2-person project, 2-person team project, that can be anything you want to do. Now, I will give you criteria. Okay, we'll talk about it on Tuesday where, this is the criteria for an A project. This is the criteria for a B and a C and so on. Okay, and we'll talk in detail about that. But anyway, it's very important to be here Tuesday if there's nothing else for this year. Then Thursday, a week from today, that's an open lab. Okay, that's just lab time for you to catch up or get ahead. Remember, lab 6 is going to be due the Friday after that. So I would imagine there'll be some people that need to work on lab 6 at that time. I won't be in the lab. I'll be available on Zoom. I'll ask the ISAs if they want to be here at least an hour or so during lab time. I may be in my office. If I am, I'll let you know. But if I'm not, I'm available on Zoom if you need help with any troubleshooting, you have any other questions. Okay, and then the last 2 weeks, the 9th and 10th weeks, those weeks are dedicated to work on the final project, right? So there's no class time. I'll be available on Zoom. Again, I'll ask the ISAs if they're available for an hour or so, maybe each day to be here in the lab. And then these are the due dates that are left. Okay, remember, tomorrow's when lab 5 is due. And then a week from tomorrow, Friday of the, let's see, that would be Friday of the 8th, right? So yeah, May 26th. So yeah, a week from tomorrow. That's when lab 6 is due. That's the sequence detector. Now, this is different. Lab 6, each person has to turn in lab 6. You can still work together, but each student needs to upload, what you've been uploading this quarter as just one submission per team. All students have to do lab 6, okay? The reason I'm doing that is to get you in the habit because the individual final project, each person's doing their own thing and turning it in, okay? And that final project individual, that's due Friday of the 9th week, okay, which is June 2nd. And then the team project, that's due the last class day of the quarter, okay, June 9th. And there is no final exam, okay? The final project is the final exam, and that's the way I look at it. I know some instructors do both, but I feel like, you had a midterm and that kind of tested your theory. Now you're going to have the project, the final project, which tests more your application and, how you can model in Verilog. Okay. So do you have any questions about just generally what's left this quarter?
The project, like every single person has to submit their own or just one person?
No, for the team project, it's just one submission per team. So yeah, the team project's just like the labs you've been doing from lab 0 to lab 5. But lab 6 and also the final project individual, that's when each person has to submit. Okay. All right, well, if there's no other questions, you have the rest of the time, work on the activity, of course, first, get that done. And then after that, the time is yours to work on whatever you need to work on, wherever you want to work on it. And Ethan should be here in about 45 minutes to help out.